Hi, welcome to today's video where we're going to be walking through how to calculate a prediction for a GLM. Feel free to pause to read the problem. I'll scroll through in chunks since there's a lot here. Alright, so first up we need to know what a link function is. And a link function, it's one of the rare moments where the name for the statistical thing is actually useful in that it is linking your linear predictor, so your x times your betas, and summing all those together. How do you link that linear predictor to the thing you actually care about, or mu? So when you build an OLS or just a linear regression model, your link function is the identity link, and that just means nothing changes. What you get is what you take out. GLMs are getting into, I want a more complicated relationship. So I have some of the notation you'll see here. So there's this eta, ETA, I had to look it up, is the notation typically used for the linear predictor, or that summation of beta times x's. And then you're trying to link mu to that. So that expected value of y. So our link function is some function of our mu, or our expected value of y, that then would equal our eta. So next is just specifically for this problem, and this is the one tricky aspect to this problem, I think, is that it does specify that it is a Probit link function. So actually, when I first read the problem, I assumed it was a logit, and I got the problem wrong, because I just assumed it's binomial target, so I assumed a logistic regression model. But Probit is when the function of a Probit is the inverse of the CDF of a normal 0, 1. So it's one of the cases where actually thinking of the inverse is a bit easier. And this is the notation you typically see with the Probit, which is this capital phi, which means the CDF. So just taking the inverse of the inverse gets you back to the CDF, and so you just say mu is the CDF of your linear predictor. And then finally, really my notation is sloppy up to this point, so there should be this epsilon for the true mu. I just didn't feel like writing it a bunch of times, and what we actually care about is our predictor, so it's not mu but mu hat, and then that's gonna be the phi of the linear predictor. So with that knowledge, we can jump into the problem. So step 1 is just calculating that linear predictor, so x times betas. First up, we have the intercept, and that's just always going to be there. And then for this problem, there's two categorical sets of variables. And when you have categorical variables, you just have all these indicators. So here we see, even though there's one variable, tenure, it has two levels, and it works out to be two indicator variables. So if tenure is less than 5, then 1, otherwise 0. And then you multiply that by its coefficient. So in this case, it's 0. And really, we're being a bit extra by writing this all out. You could look at, this is called the base level, because it's just forced to always be 0. And then if an observation deviates from the base case, that's when the prediction gets adjusted by the coefficients. So here, our base case is tenure is less than 5, or that reference level. And then if tenure is greater than or equal to 5, then that's a value of 1, and then you multiply that by the coefficient of 0.132. Exact same thing here for prior rate change. There are 3 unique levels. Being between 0 and 10 is the reference level, and then adjusted by the coefficients if the observation is one of the other 2 levels. And then finally, we actually have a continuous predictor. So that is the amount of insurance, but divided by 1,000. Is going to be multiplied by 0.0015. So this dividing by 1,000 is a bit annoying, but something you got to catch in doing the problem. So that's how that logic looks all written out. I didn't, actually solving the problem. You're not going to write that all out. Just wanted to show what's going on. But then we just plug and chug here, and so we have our intercept term. Our tenure is actually the reference level, so it's just 0. The next component is that negative 0.092, so prior rate change was greater than 10% because it was 12%. And then 225,000 divided by 1,000 is just 225 multiplied by its coefficient, because again, this is a continuous predictor. And then that finally gets us 0.6725. And what the exam writers did a really good job of was giving you a result that falls in between 0 and 1, so you might think you're done, but you're actually not. So this is just that linear predictor, and now we have to feed it into the inverse, the inverse link function to get our actual prediction. So doing that, we would go to our z table, say where at an x level of 0.6725, what is the cumulative area up to that point? And that area is approximately 7486. And when we scroll back up to the ranges for this question, the range is all the way from 0.7 to 0.8. And I'm pointing this out because when you go to your z-table for this question, you say 6725, so 0.6, 0.7, and here we see this 0.7486, but it's actually 0.6725, so it's not exactly right. So we know the actual true value is going to be in between this and this 0.7517. So the actual answer is somewhere between 0.74 and 0.75-ish. And no matter what it is in that range, it falls in the range of C for the final answer. But let's say those ranges were tighter and we needed to be more careful. If that were the case, what you can do is take a weighted average. So 0.6725 is that x value. And so we want to take a weighted average of these two numbers, but we want to give 75% of the weight to the lower one because it's closer. So to actually look up these values, so 0.67 results in this number, and that gets 75% of the weight because of how close it is versus the other value. And this is the value if you had a value of 0.68 instead of 0.67. Hope that made sense. Just taking a weighted average to try to, it's a linear interpolation between those two values and trying to approximate. I think you also might be able to just do it exactly with your calculator, so I'm not sure if you'll ever actually need to do this. Probably for the most part this is sufficient, and if that's all you did, that should be fine. So going up again, we see this falls in the range of C. So C is our final answer. As always, thanks for watching. Bye.